All right, so we're dealing with functions here. So we're going to be talking about what makes something a function. We'll look at its domain and range, and then we will also be dealing with function notation. So anyway, this has some odd problems to practice, and it has a CMHW 2.3, which I am putting is going to be due on Monday, which means I'm pretty confident that we will get through all the notes before then for sure. I won't have this class Friday unless somebody comes back and says, no, you can't do it like they did last year. So, we're supposed to do periods 1, 2, 3, 4 Thursday, and then periods 5, 6, 7, 8 Friday. Which means I'm not showing up except to the Nina at the game. Okay, so what do you know about a function? How to tell if a graph or an equation or something else actually is a function?
One x value can't have two y values.
Okay, so I usually for a function, because I don't really have a good place to write what a function is. So a function, so you're right, one x can't have two y values, or the way we tend to say is no repeating x's, which is helpful in these first two examples because they gave you a list of all the x's and they gave you a list of all the y's. But that's not super helpful if you have a graph. So how can you tell on a graph if you have a function?
The vertical line test?
Is it the vertical line test? So since you know the name of it, are you okay if we put VLT?
Yeah.
Okay, and then in parentheses, that only helps you out if you have a graph, because the vertical line test would not help you with a table. Okay, so do you know what this little guy is called?
Is it something chart?
It's actually a mapping diagram. You probably don't have to have that name. We've got a table, a mapping diagram, a couple of graphs. So we are filling out this table. So this one goes with the first column, second column, third column, fourth column, okay? So we are deciding whether it's a function, so that's just going to be a yes, no. And then we're going to look at something else, continuous and discrete, and then we're going to look at the domain and range. So do you want to just go across and answer the question function for all of them real quick? Okay, so let's examine the first one. Is it a function? Why not? Okay, so you might in parentheses say repeating, or just say repeating x's. Okay, all right. What about the second one? Okay, so what would it, wait, you're saying no, it's not a function?
Both those lines are on the zero, yes, or is one on
the 4? Okay.
I can't really tell, that line's kind of a straight.
Okay, this line is supposed to be going from the -3 to the 5.
Yeah, I get that, and I get the
This line is supposed to be going from the 0 to the -2. But even if they both pointed at the same y, that would be a repeating y. So that wouldn't change it. Yeah. So a repeating x would look like 2 arrows coming off of the same x value.
That's what I was saying. That arrow.
Oh, that one. Oh, I see what you're saying. Make it go with the 4.
Okay.
I don't know how we can do that. Yeah, somewhere
So yes.
it has slid up. I see what you're saying. Yeah.
That's what I was confused.
Yeah. So we're going to say yes. And I don't know how to fix the picture. Okay. But I do see in my notes last year, I have a little line kind of trying to drag it down to the 4. Okay. All right. So what about this one? Okay. So how does this whole vertical line test work?
Anywhere you draw a vertical line on the graph, it can't touch the function more than once.
Yes. Okay. We wouldn't call it a function because it may not be a function.
Well,
so the graph. It's just the graph. So here I've got the grid is this whole square, but the graph is just that circle. So this one's a big fat no. All right. So
I've always had heard different math teachers call those different things. Like,
Yeah.
because
Yeah, this is the grid.
some people call that the graph.
Or the coordinate. Yeah, but truly the graph is only what was drawn on the grid.
Yeah.
So the graph this is a graph of a circle sitting on top of an XY coordinate plane in grid form. And this one's not really in grid form because they didn't grid it for me with little grid lines. All right, but the graph is only a lot of times in math, they will just call the shape a curve, even if it's completely straight, but the calculator calls them curves, no matter what. So if you're trying to see if two graphs are intersecting, it'll say first curve, second curve. I'm like, but it's not a curve, it's a straight line. It doesn't care, it calls it a curve. All right, in calculus, if you are trying to graph funky things, because calculus was used to figure out how to create graphs before you could slap them in a calculator, and that whole section is called curve fitting. And they tend to be more curvy because if the function was a line, you don't need any calculus to graph that. All right, so have you heard the terms discrete and continuous ever? So how do you know the difference between those?
I always say that discrete has like exact points on the graph, and then continuous is where it goes off curve.
Okay, that's pretty good. Another way to tell if you're looking at a graph, continuous data, you should be able to trace it without ever picking up your pencil. And so there is a chunk, well, it's kind of part of the curve fitting section in calculus where you have to give an official definition of when is a graph continuous or not, or discontinuous. Like this graph is continuous all the way across the whole domain because I would never, ever, ever, ever lift up my pencil. Sometimes you get a hole in the graph. Have you ever seen a graph that just has this open circle right in the middle of the graph? You'll see it in this unit. And I would have to say it is discontinuous at that particular point. Or if it has an asymptote, it's discontinuous, so that's called a discontinuity. And we will actually talk more about the discontinuous and discontinuities, not in chapter 2, that comes up in chapter 3. Right? Discontinuities come up when you're trying to avoid dividing by 0, and we won't be graphing rational functions that have x's in the denominator until unit 3. So, anyway, so this first one, if I graphed these 4 separate points, it would be discrete. In this mapping diagram, I'm only talking about 4 points, aren't I? So it is discrete. But in this curve, it's continuous. And on the next one, it's continuous. And there are graphs that have portions that are continuous and portions that are discrete. So that's interesting. All right. If your data is discrete, then as long as they don't name like 8,000 points, when you do the domain, you would write your domain as a set. Okay? Order does not matter, but what order would you probably put the domain in? Yeah, I'm reading -1, 0, 2. Oh, wait.
You don't have to put 0.
As a matter of fact, I would count off if you did. I wouldn't count it wrong, but I'd take a point off because you should never repeat in a set. Can we come down and go ahead and get the range for that same one? Okay. 5, -3, 2, 4. I do not need these to be put in numerical order. Now, sometimes you may have a teacher that says, always put your set in numerical order just because that's easier for me to grade.
I was talking about numerical order, but if you put the domain in order, would you want the range in the same order?
No, it doesn't have to be in the -1
So it
goes
doesn't
with the
matter.
5. Yeah, because you really couldn't, because this one, that 0 went to 2 different ones.
That's why I was saying you could just put 1 and 2.
Yeah, and put them right next to each other. No, the domain and range do not have to line up in this situation, but if you are putting it in a table, you definitely want them to correspond because you're creating a bunch of ordered pairs. So, same deal going for the mapping diagram. -3049 and 0, -252. And I just put them in that order because that's the order where I saw them. But when you get to this third one, can you list every x value? No.
Numbers.
So these are best in interval notation at this level. However, if it includes all real numbers, then I would use the all real numbers symbol. So if I'm looking at this curve, it's just getting wider and wider and wider at both ends. So this one touches all the real numbers.
So does the range, right?
So does the range, because it does go down forever and it goes up forever. So there's no starting or stopping point on either of those. But when we come to that little circle there,
The domain is -3, 3, and the range is -3, 3.
inclusive, right?
Yes.
With boxy brackets, good. And the range -3 to 3 as well. Okay, so just checking that you know that. That's introduced in Algebra 1 or possibly even in 8th grade math now. And so when kids come to Algebra 2, they're still stumbling with it and learning interval notation for their first time. And by the time they get to pre-cal, that's great. All right. Now,
Fred and George.
function notation. Fred and George. Okay. So, how much do you know about this? Okay. So,
We did this for like a month.
okay. Good. Very good. Okay. For
We did
me,
functions for like ever.
many things are going to happen with this function notation in the next lessons. So it starts to get really complicated. And in calculus, you have a lot of f of x's and f of g's and f of g of x or f of g of h of x. And it can get real confusing. So when I first moved up to teaching high school and came across Algebra 2, I wasn't great at function notation, and I wasn't getting it at first. And I'm going to blame that on whoever was explaining it. I just don't think they were making it clear until it finally occurred to me exactly what all the pieces are. So I just want you to know the letter before the parentheses,
Function name.
it's the name. Okay, so algebra's favorite function name is f. They tend to put them in italics when they're using function notation so that you're not thinking this is the variable f times the variable x, but you've seen it enough that you probably recognize it. Here's my philosophy on why f is algebra's favorite function name. Because the word function starts with f. That's all I can figure. All right?
Probably.
So what's this?
The variable?
It is the variable, and it's the variable that you can expect to be used on the other side of the equation. Okay, so if it's f of x, I'm not expecting to see other variables other than the x. So anyway, do you know what you call this side of the equation? Okay, it is the function rule.
I've heard that.
Okay, so here's my little story. Have I given you any of my story about Fred and
I
George?
think so. I think you gave it to us last year. A little bit.
Did we talk about it? I
Yeah,
don't
we
even
did
remember
functions
Fred and
last
George
year.
coming up at all.
It was like very beginning.
Okay. And all right, so
Give me
anyway,
the rundown.
it may have been that somebody needed it for the college careers or something. I don't know.
No, we did functions. There was a unit over functions, and it wasn't like a detailed unit, but we did. It was really for solution sets when we were writing solution sets and stuff like that.
Oh,
We
okay.
used functions.
Oh, okay, gotcha. I don't remember, and I haven't taught that class enough that I can remember what's next. And
Really?
you know, eventually, now it's kind of funny because the other night I was trying to think about this class, and I was going, "What is Unit 4 about?" I can tell you every lesson that's in Unit 3, and I can tell you what's in Unit 5, and I am drawing a complete blank on 4, and that actually bothers me. So where is Unit 4? It is algebras are new to.
Oh,
So you have
geez.
to have inverses and
Hated those.
logarithms and exponentials. That's it. For the life of me, it was just nowhere in my brain. After, I think I've been doing that book for over 10 years now. And so that one just left me completely. Okay, but it was in the middle of the night. All right, so my little story, Fred and George. Fred and George, well, we're going to start off with Fred. Fred, most popular kid in the entire high school. Everybody loves him because he's so good at math. Fantasy world I live in, right? And so everybody's always throwing math problems at him, so Fred comes up with this little game where he comes up with a function rule every morning, picks a favorite function rule that he loves, and that's in his head. In his head, brain's like a computer. He's walking down the hall with this rule in his head, and everybody loves Fred. So Fred's coming down the hall. You see all the freshmen going, "There's Fred, Fred, give him a number, give him a number, give him a number." They shove one of their little buddies out in front of him. Fred. So then he has to call Fred's name, and then he throws a number at him, and Fred plugs it in. As you plug in things to function rules, I recommend that you put, so what's Fred's rule here? You would want to say that, wouldn't you? But I always say -3 times something plus 4, okay? And the more you play with the story and you let the story develop this year, in calculus, you will be able to pull up what you know about Fred and George, and it may just save your tail. So, anyway, so Fred's waiting for input. So, in this case, this problem is a little kid calls Fred by name and gives him an input. And so Fred puts it into his rule, and Fred's rule is -3 times something plus 4, right? So if the kid throws a -3 at him, I would put it in parentheses. And let me tell you there's sometimes I don't bother putting it in parentheses. But if there's a coefficient in front of the x, put a parentheses. If there's a power on the x, put the input in the parentheses and the power on the outside. So the parentheses would just surround the x. Also, if there's a negative right in front of it, probably a good idea to put parentheses, okay? But if I had 4 plus x, I probably wouldn't put a parentheses on front of x. All right, and so inside of Fred's head, he computes
13.
And yes, comes up with a 13. So the 13 comes out of Fred's mouth as the output, and the input comes out of the little kid who wants to play with Fred, right? Okay, so after Fred has this going for a few weeks, his best friend, George, comes to him and he said, "Dude, I'm really good at math too. Fred's the king. So Fred's like #1 in UIL math in the state. But his best friend George always comes in second. It's only like a point or two behind him. And on the math team together, they just sweep everything. And George comes to Fred and he says, "Dude, I'm kind of ashamed of myself, but I am so jealous. You are getting so much attention with your math skills, and nobody knows about my math skills. And I was just wondering if there are ways that you could work me into the game." And Fred goes, "Oh, the possibilities. Yes, here's what you got to do. I need you to go home every morning, wake up, just come up with a function rule." Well, George is kind of having to regain some face here. He's kind of been, so he tends to, in all the book examples and every curriculum I've ever had, George has a tendency to go a little extra. Fred may come up with a simple function, but George just goes all insane. So George's function rule here is, in this case, I wouldn't say negative. What would you probably hear me say? The opposite of something squared plus 4 times something plus 1. So George is walking down the hall, and inside his head, he's saying the opposite of something squared plus 4 times something plus 1, and he's waiting for somebody to throw something at him, right? And so all the kids are throwing numbers, right? And so he's in the cafeteria, walks in the cafeteria, George and Fred walk in, and he's like, "Oh, it's George and Fred," and all eyes point over at him, and there's a bunch of freshmen over there, and the kids, they shove their friend out, so you do it, no, you do it, no, you do it, no, you do it. And they shove him out, and they yell, "Hey, George!" And George turns around, and he sees this kid, and the kid's nervous, and the whole cafeteria is just close and walking. And he says, "You got an input for me, buddy?" And the kid is so nervous, he opens his mouth, and the number doesn't come out. What comes out? K. So he goes, K. And at that moment, it's like a pivotal moment in that kid's life. He is about to die of embarrassment. So there's a split moment where he says, K! And then you can already hear the laughter starting to ripple through, and his buddies are just a little bit in shock, but they are about, what did you do? And George and Fred, not only did we get that, they're amazing human beings. So George has about half a second to save that kid's social life. He could crush him so bad. He could say, "What? That's a phone number?" But no, George is not that type of person. So he sees it in the kid's eye. The kid's going like this, and you can already see the tears rolling up. The kid is thinking, "I'm going to have to move. I have to go somewhere else." And George, you be the kid. So he said, "Hey, George. Hey, George.
Hey.
Oh, I see what you're doing. Put it here, buddy. Nobody has ever given me a variable before. That is so. Do it again. Do it again." And so now the whole cafeteria is going, "Man, he just did something dumb." And the coolest kid in school saying he's brilliant. Well, I want to give him a letter now. And so George then computes with a letter. Well, since he had a variable as the input, he can't just give a constant as an output. He's just going to put that K right in his massive brain, and he's going to rewrite it, and he's going to have to give him an algebraic expression because he still has a variable in there. So the kid did a variable switch on. So, man, nobody's ever pulled a variable switch on me. Oh, you're brilliant, aren't you? You're the math team. And the kid is there trying to think, I hope the tears don't fall. And he's completely safe. And now all of his buddies are patting him on the back, and the whole rest of the day, like, "Man, that was brave. Yeah. Anyway, so great stuff happening in the high school with Fred and George. So, what does George say? So, what would
Negative K squared plus 4K plus 1.
Plus 4K plus 1. Oh, there's your output right there. Okay? So now everybody wants to try to wow Fred and George. So this kid throws a binomial at Fred. He says, "Hey, Fred, 3t minus 2. So he's doing a variable switch and throwing in other stuff. Now, what is Fred's rule?
3x.
Be careful, there's a negative in front of it.
Yeah.
So negative 3 times something, but I'm going to have to make my something parentheses fat enough to stuff a binomial in there, right? And then a plus 4, correct? And we're throwing 3t minus 2 inside of that, and we won't be able to come up with a constant because we still have a variable. So if you clean it all up, what you get?
Negative 9t plus 2.
T is not my favorite variable, so I always curve it on the bottom so I don't mix it up with plus signs. So that's just the beginning here. We are going to use this function notation in multiple ways in the coming weeks. And sometimes you get to know, like we knew right here, like, where did both of my yellow highlighters go? This guy likes to live on the floor. And I don't know where my clicky yellow highlighters are over here. Anyway, I'm going to come back and highlight these because that got very busy. Sometimes we get a glimpse inside the function guys' heads and we get to see their rule, and then we can plug into it. Sometimes we do not get to glimpse inside of their heads. We've been given one of these mapping diagrams. We don't know Fred's rule. But we know how the game goes, right? So this isn't Fred's head. In my story, because my story has to develop well. So good and well, at some high school, if Fred and George are walking around giving inputs and outputs, there's always the haters, right? The naysayers. There's going to be the people that are so jealous of Fred and George, they're always walking around going, they're just making stuff up. Oh, look, I'm Fred, so I'm written. Oh, 72. Oh, worship me. You know that kid's there, right? So these naysayers are trying to prove that Fred and George are full of baloney. So they start stalking Fred and George with clipboards, and they record inputs and outputs, trying to see if during the day somebody inputs the same number and Fred gives different outputs. If that's the case, Fred's not functioning, is he? Okay? So now these naysayers are not all that bright, or they just join them and be on the math team and be happy like Fred and George are, but they're not that bright. And so they record their data. I think if I was going to be stalking, I would record all my data in a table. That would be a wonderful way to record this. But no, one of the guys is making a mapping diagram, and another one just graphs all the points. Plays connect the dots to see if it fails the vertical line test somewhere. So on one particular day, a kid says, hey, Fred. What's the kid throw at Fred? A 1. But you're wanting to know what Fred said, and, because you're in the fan club following around, you want to hear Fred's response. But right when Fred opens his mouth to answer, you sneeze. Have you ever noticed that while you're sneezing, you can't hear things? So you miss it, and you're like, what'd they say? What'd they say? And then you see the little stalker, and you go, hey, which is not okay. What did he say? So how can we read his information?
Follow the arrows.
Huh?
Follow the arrows.
Oh, follow the arrows. And so when the input was 1, the output was? Good deal. Same on a graph. But now you're looking for a point that has and your inputs are your x's, right? Mm-hmm. So input -2. This is a very dark graph. Can you even find it?
Yes.
This is the point where x was -2. What's the y value? +2. So you've seen it with graphs, right? Perfect. So let's carry on. Let's move to...
The book is wrong. Don't trust.
Okay. This is important. This is very important. And I'll tell you, have you heard me talk about Ricky Ryan ever before, my math guru? Okay. So the day that I was teaching out of this book for the first time, that week, Ricky Ryan's wife was sick and in the hospital for a whole week. And I get to this, and I'm looking at the answers that my book is giving me, and I'm like, this doesn't seem right. And but Ricky wasn't there for me to ask. So I had to go ask a physics teacher, and we both came to the conclusion that the book was wrong. But most of the time when I'm sure the book is wrong, it's not the book is wrong. These people, they're way more brilliant than I am at math. Okay, so the book is wrong. When you see directions telling you to give the intervals that a graph is increasing, decreasing, or constant, do not trust the answer key. We will never use inclusive boxy brackets. No. When you are asked the intervals for increasing, decreasing, and constant, we will use parentheses always. The book is wrong. Okay? Do I need to say it again? We got that. Okay. This is the type of graph you might see in calculus in curve fitting at some point. It's doing some increasing in some places, it's doing some decreasing in some places, it's doing some being constant in some places. How are you going to tell the difference between increasing, decreasing, and constant?
When it's increasing, it's going up.
It's going up. Decreasing, it's
going down.
And constant, it's
going
flat. That's not very flat. Okay. So if I'm looking at this graph, I can kind of separate it into parts. I'm going to use this sticky note thing kind of as a straight edge. So if I was following this graph, by the way, it looks like it is going straight up, but it's a function. So it's just getting wider and wider and wider. So the first interval has been going from negative infinity, okay? But it's going down until right about there. Okay, so I'm just going to put a dotted line to kind of separate. I've been decreasing for a while, haven't I? Okay, and then at that particular point, I shift directions and I start doing what? Okay, and I increase for a couple of spaces until I'm at the x value of negative 2. By the way, the intervals will be your x values, not how high it goes, but where is it going up and where is it going down along the x-axis. And then right after I pass up that negative 2, what happens? Okay, until you hit the x value of 0, right? And then what happens for a while? Okay, I'm going to split because we have a new thing happening, and then for a little while it does what? It increases again, right? So we were decreasing, increasing, decreasing, constant. I don't have a great abbreviation for constant. And then we did some increasing, correct? So this is the type of problem you will have. Determine the intervals of the domain, which means x values, for this the function. Does it really say that? Determine the intervals of the domain for this the function is. I don't know what it's supposed to say, but that's no good. For which the function maybe? For which the function is 10 years of these notes, and nobody's ever caught that. Increasing, decreasing, and constant. So let's get all of our increasing. How many increasing intervals do we have? 2. So using my skewer of knowledge, where did that first interval begin? And you might want to say, hey, it's not an open circle at negative 4, so I should include it. But wait, never include when you see the words increasing and decreasing. And here's the reason. Because at that point, I'm not necessarily part of the decreasing side or the increasing side. In calculus, and this is a big part of that first part in calculus where I talked about derivatives. Derivatives tell you the slope. We're used to slope only with straight lines. But in this graph, where it's decreasing, every point has a slope that's negative. And when it starts going back up, the slope becomes positive. But at that point in between, that slope is 0. So it's not negative or positive. Okay? So from negative 4 to negative 2, we were increasing. And then we have a gap before that happens again, so I might put a union with my next interval, but I think the book may not even bother to put a union. It may just put a comma. But I think a union is very appropriate there. So where else are we increasing? 4 to 7. Good. So you're only getting x values off the x-axis to put your numbers down. All right, so how many decreasing intervals do we have? 2. So on that first one, where did it start decreasing? Good, good, good. And it stopped decreasing at, and we didn't include that negative 4 in neither the increasing or the decreasing, did we? And we have a gap, so I'm going to put a union. And when did the decreasing start again? Through 0. Good. And how many constant intervals do we have? We just have 1. So we are constant from 0 to 4. So did you do increasing, decreasing, constant in algebra 2? Okay, great. Love that is this case. All right. So now, using the same graph, let's do some Fred. This is Fred's graph. Notice it says y equals f of x. It's Fred's graph. So if the input's negative 4, what's the output on that graph? What about when the input is 7? What about when the input is 4? Are you sure?
No, but it doesn't include it.
So I can say that when I input a 7, Fred gave the answer of a fine. But when you input a 4, there's an open circle there. What does that mean? Fred didn't give an answer. He didn't define an output. It is undefined. Undefined will happen if the graph just stops. So what if I said, hey, Fred ate? Okay, so Fred has restricted this domain. Okay, this is not the graph of any one function. This is a piecewise graph. If you had to give this function, Fred had part of a parabola here, and then a piece of an upside down parabola, and part of a horizontal line, and part of a positively sloping line. But he decided not to include the number 4 in his domain, and also not to include anything that was greater than 7 in his domain. But he did include something equal to 7. So you may have undefined for some parts of a domain because there have been domain restrictions. All right? And that literally is all the notes I have for 2.3. So let's go back to, you have a 2.3 assignment, and that'll be due Monday. All right? So we're going to go right into 2.4 and 2.5. So the book made 2.4 and 2.5 two separate lessons, but they all are about lines. So I'm cramming them together. Okay? So 2.4.5, I'm going to have you expect a quiz over all the skills that were covered in these notes. Okay? So we're just pretty much going back to, actually it goes before Algebra 1. Used to, you learned about y equals mx plus b in Algebra 1 for the first time. Now that's actually 8th grade math. In Algebra 1, they find out about standard form and point slope form and other forms like that. But anyway, all of it gets covered again in Algebra 2, and then we're just refreshing. Okay? So it's all about lines, and we have several formulas. So, do you recall the slope formula? When would you use this formula?
I can graph from 2 points.
Okay, so if you've been given 2 points and you need to know their slope. Okay, now, why do you need to know this again? Calculus is very heavily based on this slope formula. When you learn derivatives, it's the slope of curves. But you might get the slope of what is called a secant line. So, which means they pick 2 points and you find the slope. You will, in calculus, not often, but there will be times in calculus that your instructions are to write the equation of the line. And it will tell you a point that it passes through, and you'll have to use some calculus to find the slope. So, anyway, totally familiar with this, right? Have you ever seen this OK and this NO? The big OK and the big NO. Okay, wasn't it? No, I didn't know what you were saying.
I said it, sorry.
Okay, so if you are using this formula and the two y values are exactly the same, when you subtract them, you're going to get a 0. It is okay to have a 0 on top when you're dividing. If you try to put a 0 divided by something in the calculator, it just gives you 0, right? But it's a big fat NO in algebra if you put the 0 on the bottom, right? So if the x values match, then you will get a 0 on the bottom. If the x values match, you don't even have a function, do you? And it is undefined. Notice how I typed the undefined up and down, because an undefined line goes straight up and down. So that's just a nice way to remember, especially when you get a bunch of algebra students that think you can always divide by 0 and you can't. Okay, next thing, the slope is often called, and this is going to be important because they will use these words in one of your word problems. It is called the average rate of, do you know what's going to be? Change. So you've heard of rate of change before, right? In a line, there is a constant rate of change. The slope is sometimes called the constant rate of change. But in a situation where it may change from minute to minute, like your speed, that rate of change, your speed is not always constant when you're driving your car. It goes up and it goes down. But slope is sometimes called the average rate of change. If you see the words average rate of change in a word column, they're going to give you 2 points, and you're using this formula to find out that average rate of change, because they give you 2 data points. Are you pretty familiar with point slope form? In calculus, depending on your teacher, if they tell you to write a line, to make the equation of a line, they are usually happy if you leave it in point slope form, because you are going to be given a point and you're going to be finding a slope, and so this is your best form for it. And then generally they're happy if you just stop there and even make you change it to slope intercept or standard form. But we do have slope intercept form, which is the friendliest form for getting a line onto a graph, and we have standard form. Standard form just fits some word problems nicely. So you have your x's and y's on the left and your constant on the right. But there's some restrictions on what can happen with this. There's 2 restrictions in standard form. Do you know what you're not allowed to have in standard form?
Negatives.
Okay. No leading negative. So the a value, your x coefficient, cannot be negative. So you may find that you do have a leading negative and you just need to multiply through by a negative and change all the signs. There's also something else that shouldn't show up in standard form. No blanks or blanks. I'll give you one of them. Fractions.
Decimals?
Yeah. So standard form wants to be prettier. It's very rare for you to even see decimals in standard form. You may have an equation written in standard form that money was involved, but nobody's calling it standard form. But you don't, when your instructions are write this in standard form, then no fractions. So that means if you get everything in order and it says negative 3/4 x plus 2y equals 7, you're going to have to multiply by a negative 4 to clear that denominator and get rid of the negative sign. All right? Do you understand both of you are falling over and dying? Okay. Now, in some of the problems you're doing out of the book and possibly on my quiz, it will specify finish the problem in such and such form. So make sure you're reading the directions. I think in the book problems it says in problems something through something, write the answer in standard form, and in problem something through something, write it in slope intercept form. So you just have to notice when you switch to the new numbers. All right, what do algebra students know about parallel lines and perpendicular lines? What do you know about parallel and perpendicular?
Parallel lines can never touch.
Ah, very good. And what do you know about perpendicular lines?
They always make a line.
Okay, so that is what 5th graders know about parallel and perpendicular lines. Algebra students know that that means their slopes are somehow related. So what do we know about the slopes of parallel lines?
They're the same.
Same slope. So we love to ask students to give the equation of a line that passes through point 32 and is parallel to this totally unrelated line. Okay? What do you know about the perpendicular line's slopes? There's 2 pieces of information, 2 things you have to do. They are opposite, meaning you change the sign. Okay. Let me go up and put a little bit more with same slope. So up here by parallel. Let's say that I tell you to make a line that's parallel to a line that has a slope of 3 halves. This is the symbol for parallel. So what would the slope be in a line that is parallel to that one? 3.5. Good. Let's say I want perpendicular, and I say the first line has a slope of 3/2. Do you know what the symbol for perpendicular is? It's an upside down capital T. Okay, because they make right angles, right? So, what would the slope be that is perpendicular to 3/2?
So it'll be negative.
You do something else with that fraction.
Don't you switch it?
What's it called when you switch?
The conjugate?
No.
Reciprocal.
Okay. So
then what's a conjugate?
Conjugate is when you take a binomial and you change the sign in the middle, like in a dots situation.
Oh, okay.
You're like, I know that's a thing.
I need the same thing in my brain though.
Yeah,
Switching it, so
and they are not. Okay. And we can't even say a conjugate is opposite because you don't change both
We've
sides.
had this conversation before.
Yep, we have. All right. So now, one thing kind of interesting. What if my slope was 4? What would the perpendicular slope be to 4?
Negative 1/4.
Good job. All right. Now, have you ever heard Hoy-Vux? Okay. So I learned Hoy-Vux at the same time that I learned this OK and an O, and I don't remember where I was. They just appeared in my knowledge bank, my toolkit, on the same week. And I don't know if I just stumbled across them on the internet or if I was in a workshop and somebody taught me those, but I will say that I was teaching Algebra 2 at the time, and I was in my linear unit on Algebra 2, and I had already taught about horizontal and vertical lines, and my students were blowing it all over the place. And then I found this Hoy-Vux, so I tried to go back and show them this better way, and they couldn't, they rejected it. But the next year it was in my notes. So that's the end. So we will start with Hoy-Vux next time. All right. So Pat, we'll read this. And I need to get this video uploading, so I'm going to leave it to you to get the door.